Today we'll program a guessing game entirely in Rust. Let's go. Let's jump into Rust by working through a hands-on project together. This chapter introduces you to a few common Rust concepts by showing you how to use them in a real program. You'll learn about let, match, methods, associated functions, external crates, and more in the following chapters. We'll explore these ideas in more details. In this chapter, you'll just practice the fundamentals. We'll implement a classic beginner programming problem, a guessing game. Here's how it works. The program will generate a random integer between 1 and 100. It will then prompt the player to enter a guess. After a guess is entered, the program will indicate whether the guess is too low or too high. If the guess is correct, the game will print a congratulatory message and exit. Setting up a new project. To set up a new project, go to the projects directory that you created in chapter 1 and make a new project using cargo, like so. Okay? So cargo, new guessing game, then cd to guessing game, and then we need to open this with yeah, it's open now. The first command, cargo new, takes the name of the project guessing game as the first argument. The second command changes to the new projects directory. Look at the generated cargo toml file. I see it. As you saw in chapter 1, cargo new generates a hello world program for you. Check out the source main.file. Now let's compile this hello world program and run it in the same step using the cargo run. All right, cargo run. Yep, fantastic. The run command comes in handy when you need to rapidly iterate on a project, as we'll do in this game, quickly testing each iteration before moving on to the next one. Yeah. Reopen the source/main.rs file. You'll be writing all the code in this file. Check. Processing a guess. The first part of the guessing game program will ask for user input. Process that input and check that the input is in the expected form. To start, we'll allow the player to input a guess. Enter the code in listing to 1 into source main. All right, so it's just asking us to do copy pasta and then it will break it down. Let's do as they say. This code contains a lot of information, so let's go over it line by line. To obtain a user input and then print the result as output, we need to bring in the IO input-output library into scope. The IO library comes from the standard library known as STD, sexual transmitted disease. Right, or standard. It depends of, whatever you want to use. By default, Rust has a set of items defined in the standard library that it brings into the scope of every program. This set is called the prelude, and you can see everything in it in the standard library documentation. If a type you want to use isn't in the prelude, you have to bring that type into scope explicitly with a use statement. Using the standard IO library provides you with a number of useful features, including the ability to accept user input. As you saw in chapter 1, the main function is the entry point into the program. Wow, amazing. fn syntax declares a new function. The parentheses indicate there are no parameters, and the curly bracket starts the body of the function. As you learned in chapter 1, println bank is a macro that brings a string to the screen. This code is printing a prompt stating what the game is and requesting input from the user. Storing values with variables. Next, we'll create a variable to store the user input, like this. Great. Now the program is getting interesting, you bet. There's a lot going on in this little line. We use the let statement to create the variable. Here's another example. Let apples equals 5. This line creates a new variable named apples and binds into the value 5. In Rust, variables are immutable by default, meaning once we give the variable a value, the value won't change. We'll be discussing this concept in detail in the variables and mutability sections in chapter 3. To make a variable mutable, we add mute before the variable name. Now the // syntax starts a comment that continues until the end of the line. Rust ignores everything in comments. We'll discuss comments in more detail in chapter 3. Returning to the guessing game program, you now know that let mute guess will introduce a mutable variable named guess. The equal sign tells Rust we want to bind something to the variable now. On the right side of the equal sign is the value that guess is bound to, which is the result of calling string new, a function that returns a new instance of a string. String is a type provided by the standard library that is grabbable UTF-8 encoded bit of text. The colon syntax in the new indicates that the new is an associated function of the string type. An associated function is a function that's implemented on a type, in this case string. This new function creates a new empty string. You'll find a new function on many types because it's a common name for a function that makes a new value of some kind. Full. The let mute guess equals string new line has created a mutable variable that is currently bound to a new empty instance of a string. Phew. Receiving user input. Recall that we included the input-output functionality from the standard library we use standard IO on the first line of the program. Now we'll call the standard in function from the IO module, which will allow us to handle user input. If we hadn't imported the IO library with the use standard IO at the beginning of the program, we could still use the function by writing this function call as standard IO standard in. The standard in function returns an instance of standard in, which is a type that represents a handle to the standard input for your terminal. Next, the line readLine calls the readLine method on the standard input handle to get input from the user. We are also passing guess as the argument to readLine to tell it what string to store the user input in. The full job of readLine is to take whatever the user types into standard input and append that into a string without overwriting its contents. So we therefore pass that string as an argument. The string argument needs to be mutable, so the method can change the string's content. The ampersand indicates that this argument is a reference, which gives you a way to let multiple parts of your code access one piece of data without needing to copy that data into memory multiple times. References are a complex feature, and one of Rust's major advantages is how safe and easy it is to use references. You don't need to follow a lot of those details to finish this program. For now, all you need to know is that, like variables, references are immutable by default. Hence, you need to write &mute guessed rather than &guessed to make it mutable. Chapter 4 will explain references more thoroughly. Okay, this next part is extremely useful, so please pay attention. Handling potential failure with result. This is one of the major Rust building blocks, in my opinion. We are still working on this line of code. We are now discussing a third line of text, but note that it is still part of a single logical line of code. The next part is this method. Expect fail to start line. We could have written this code as just like one line, standard in, readLine, and then the expect statement. However, one long line is difficult to read, so it's best to divide it. It's often wise to introduce a new line and other white space to help break up long lines when you call a method with the method name syntax. Now let's discuss what this line does. As mentioned earlier, readLine puts whatever the user enters into the string we pass to it, but it also returns a result value. Result is an enumeration, often called an enum, which is a type that can be in one of multiple possible states. We call each possible state with a variant. Chapter 6 will cover enums in more detail. The purpose of these result types is to encode error handling information. So similar to like JavaScript try-catch blocks and stuff like that. Results variants are OK and error. The OK variant indicates the operation was successful, and inside OK is the successfully generated value. The error variant means that the operation failed, and error contains information about how or why the operation failed. Values of the result type, like values of any type, have methods defined on them. An instance of result has an expect method that you can call. If this instance of result is an error value, expect will cause the program to crash and display the message that you passed as an argument to expect. If the readLine method returns an error, It will likely be the result of an error coming from the underlying operating system. If this instance of result is an OK value, expect will take the return value that OK is holding and return just that value to you so that you can use it. In this case, that value is the number of bytes in the user's input. If you don't call expect, the program will compile, but you will get a warning. And the warning is that you are not using the result of readline. Rust warns you that you haven't used the result value returned from readline, indicating that the program hasn't handled a possible error. So in Rust, we don't like that, to be honest with you. We just don't. The right way to suppress the warning is to actually write error handling code. But in our case, we just want to crash this program when a problem occurs, so we can use expect. You'll learn about recovering from errors in Chapter 9. Printing values with printline placeholders. Aside from the closing curly bracket, there's only one more line to discuss in the code so far. This line prints the string that now contains the user's input. The set of curly brackets is a placeholder. Think of curly brackets as a little crab pincers that hold a value in place. When printing the value of a variable, the variable name can go inside the curly brackets. When printing the result of evaluating an expression, place empty curly brackets in the format string, then follow the format string with a comma-separated list of expressions to print each empty curly bracket placeholder in the same order. Printing a variable and the result of an expression in one call to print line will look like this. Alright, so let x equals 5, let y equals 10, and then here we are printing both variables using two styles. Putting the variable within the curly brackets and as part of the comma-separated list of expressions. This code will print x equals 5 and y plus 2 equals 12. Testing the first part. Let's test the first part of the guessing game. Run it using cargo run. We did that already, I think. No, we didn't. Cargo run. Guess the number. I'll just put 6 so that it matches this. At this point, the first part of the game is done. We are getting input from the keyboard and then printing it. Generating a secret number. Next, we need to generate a secret number that the user will try to guess. The secret number should be different every time so the game is fun to play more than once. We'll use a random number between 1 and 100 so the game isn't too difficult. Rust doesn't yet include a random numbered functionality in its standard library. However, the Rust team does provide a rand crate with set functionality. Using a crate to get more functionality. Remember that a crate is a collection of Rust source code files. The project we have been building is a binary crate, which is an executable. The rand crate is a library crate, which contains code that is intended to be used in other programs and can be executed on its own. Cargo's coordination of external crates is where Cargo really shines. Before we can write code that uses rand, we need to modify the Cargo TOML file to include the rand crate as a dependency. Open that file now and add the following line to the bottom beneath the dependencies section header that Cargo created for you. So cargo.toml rand equals to 0.8.5. In the Cargo TOML file, everything that follows a header is part of that section that continues until another section starts. In dependencies, you tell Cargo which external crates your project depends on and which version of those crates you require. In this case, we specify the rand crate with the semantic version specifier 0.8.5. Cargo understands semantic versioning, sometimes called semver, which is a standard for writing version numbers. The specifier 0.8.5 is actually shorthand for caret 0.8.5, which means any version that is at least 0.8.5 but below 0.9.0. Cargo considers these versions to have public APIs compatible with version 0.8.5, and this specification ensures you'll get the latest patch releases that will still compile with the code in this chapter. Any version 0.9.0 or greater is not guaranteed to have the same API as what the following examples use. Now, without changing any of the code, let's build the project. Okay, so cargo build. Cool. You may see different version numbers, but they will all be compatible with the code thanks to semantic versioning, and different lines depending on the operating system, and the lines may be in a different order. When we include an external dependency, Cargo fetches the latest version of everything that dependency needs from the registry, which is a copy of data from crates.io. Crates.io is where people in the Rust ecosystem post their open source Rust projects for others to use. After updating the registry, Cargo checks the dependencies section and downloads any crates listed that aren't already downloaded. In this case, although we only listed rand as a dependency, Cargo also grabbed other crates that rand depends on to work. After downloading the crates, Rust compiles them and then compiles the project with the dependencies available. If you immediately run cargo build again without making any changes, you won't get any output aside from the finished line. Cargo knows it has already downloaded and compiled the dependencies, and you haven't changed anything about them in your cargo.toml file. Cargo also knows that you haven't changed anything about your code, so it doesn't recompile that either. With nothing to do, it simply exists. If you open the search/main.rs file, make a trivial change, and then save it and build it again, you'll see only 2 lines of output. Alright, so I'll trust you. These lines show that Cargo only updates the build with your tiny change to the source main file. Your dependencies haven't changed, so Cargo knows it can reuse what it has already downloaded and compile for those. Ensuring reproducible builds with the cargo.log file. Cargo has a mechanism that ensures you can rebuild the same artifact every time you or anyone else builds your code. Cargo will use only the versions of the dependencies you specified until you indicate otherwise. For example, say that the next week version 0.8.6 of the rand crate comes out, and that version contains an important bug fix, but it also contains a regression that will break your code. To handle this, Rust creates the cargo.log file the first time you run cargo build. So we now have this in the guessing game directory. When you build a project for the first time, Cargo figures out all the versions of the dependencies that fit their criteria and then writes them to the cargo.log file. When you build your project in the future, Cargo will see that the cargo.log file exists and will use the versions specified there rather than doing all the work of figuring out versions again. This lets you have reproducible builds automatically. In other words, your project will remain at 0.8.5 until you explicitly upgrade, thanks to the cargo.log file. Because the cargo.log file is important for reproducible builds, it is often checked into source control with the rest of the code in your project. Updating a crate to get a new version. When you do want to upgrade a crate, Cargo provides the command update, which will ignore the cargo.log file and figure out the latest versions that fit your specifications in cargo.toml. Cargo will then write those versions to the cargo.log file. In this case, Cargo will only look for versions greater than 0.8.5 and less than 0.9.0. If the rand crate has released the 2 new versions 0.8.6 and 0.9.0, you will see the following if you ran cargo update. Cargo ignores the 0.9.0 release. At this point, you will also notice a change to your cargo.log file, noting that the version of the rand crate that you are now using is 0.8.6. To use the rand version 0.9.0 or any version in the 0.9.x series, you'll have to update the cargo.toml file to look like this instead. The next time you run cargo.build, Cargo will update the registry of crates available and reevaluate your rand requirements according to the new version you have specified. There's a lot more to say about Cargo and its ecosystem, which we'll discuss in Chapter 14. But for now, that's all you need to know. Cargo makes it very easy to reuse libraries, so Rustaceans are able to write smaller projects that are assembled from a number of packages, generating a random number. Let's start using rand to generate a number to guess. Next step is to update source main.rs as shown in listing 2-3. And then what we see is that there are some updates. Let's see. So first thing we see is that there's a new import, and then there's a secret number that gets generated. How does it know the range? Probably because a lot of people type the same. So now it knows. So 1, 2, 100 inclusive. That's what that means. First, we add the line use rand : RNG. The RNG trait defines methods that random number generators implement. And this trait must be in scope for us to use those methods. Chapter 10 will cover traits in detail. Next, we are adding 2 lines in the middle. In the first line, we call the rand : thread RNG function that gives us the particular random number generator we are going to use, one that is local to the current thread of execution and seeded by the operating system. Then we call the genRange method on the random number generator. This method is defined by the RNG trait that we brought into scope with the use rand RNG statement. The genRange method takes a range expression as an argument and generates a random number in the range. The kind of range expression we are using here takes the form start ... equals to end, and it is inclusive on the lower and upper bounds. So we need to specify 1 ... equal 100 to request a number between 1 and 100. Note: you won't just know which traits to use and which methods and functions to call from a crate. So each crate has documentation with instructions for using it. Another neat feature of Cargo is that running the cargo doc -- open command will build the documentation provided by all your dependencies locally and open it in your browser. If you are interested in other functionality in the rand crate, for example, run cargo doc -- open and click rand in the sidebar on the left. The second new line prints the secret number. This is useful while we are developing the program to be able to test it, but we will delete it from the final version. It's not much of a game if the program prints the answer as soon as it starts. True. So where are we printing it? Oh, I think I missed that part. I'll just add it here. Then what? Cargo run. All right. Try running the program a few times. You should get different random numbers, and they should all be numbers between 1 and 100. Great job. Yeah, petty. Petty. Comparing the guess to the secret number. Now that we have user input and a random number, we can compare them. That step is shown in listing 2-4. Note that the code won't compile just yet, as we will explain. They are adding a match statement, and this won't work, so I won't even bother. First, we have another use statement, bringing a type called standard CMP ordering into scope from the standard library. The ordering type is another enum and has the variants less, greater, and equal. These are the 3 outcomes that are possible when you compare 2 values. Then we add 5 new lines at the bottom that use the ordering type. The CMP method compares 2 values and can be called on anything that can be compared. It takes a reference to whatever you want to compare with. Here it's comparing guess to secret number. Then it returns a variant of the ordering enum we brought into the scope with the use statement. We use a match expression to decide what to do next based on which variant of the ordering was returned from the call to CMP, with the values in guess and secret number. Let me just put the code there so that you see what this is talking about. A match expression is made out of arms. An arm consists of a pattern to match against, and the code that should be run if the value given to match fits that arm's pattern. Rust takes the value given to match and looks through each arm pattern in turn, so top to bottom. Patterns and the match construct are powerful Rust features. They let you express a variety of situations your code might encounter, and they make sure you handle them all. These features will be covered in detail in Chapter 6 and Chapter 18 respectively. Let's walk through an example with the match expression we used here. Say that the user has guessed 50 and the randomly generated secret number this time is 38. When the code compares 50 to 38, the CMP method will return ordering greater because 50 is greater than 38. The match expression gets the ordering : greater value and starts checking each arm's pattern. It looks at the first arm pattern, ordering : less, and sees that the value ordering greater does not match ordering less. So it ignores the code in that arm and moves on to the next arm. The next arm's pattern is greater, which does match greater. The associated code in that arm will execute and print too big to the screen. The match expression ends after the first successful match, so it won't look at the last arm in this scenario. However, the code in listing 2-4 won't compile yet. Let's try it. Oh, I see. So the types are off. The core of the error states that there are mismatched types. Rust has a strong static type system. However, it also has type inference. When we wrote letMuteGuess equals to string new, Rust was able to infer that guess should be a string and didn't make us write the type. The secret number, on the other hand, is a number type. A few Rust number types can have a value between 1 and 100. I32, a 32-bit number, U32, an unsigned 32-bit number, I64, a 64-bit number, as well as others. Unless otherwise specified, Rust defaults to an I32, which is the type of secret number unless you add type information elsewhere that will cause Rust to infer a different numerical type. The reason for the error is that Rust cannot compare a string and a number type. Fair enough. Ultimately, we want to convert the string the program reads as input into a number type so that we can compare it numerically to the secret number. We do so by adding this line to the main function body. Okay, I like it. Let guess. Well, AI to the rescue. So we trim the input and then parse it, and because we are saying that we expect an unsigned 32 back, then it will just do it, all throw an exception, throw an error. We create a variable named guess. But wait, doesn't the program already have a variable named guess? It does, but helpfully Rust allows us to shadow the previous value of guess with a new one. I know that that's frowned upon in other languages, but here in Rust we love that stuff. Shadowing lets us reuse the guess variable named rather than forcing us to create two unique variables, such as guess stir and guess, for example. We'll cover these more in detail in chapter 3, but for now, know that this feature is often used when you want to convert the value from one type to another type. We bind this new variable to the expression guess trim parse. The guess in the expression refers to the original guess variable that contained the input as a string. The trim method on a string instance will eliminate any white space at the beginning and end, which we must do to be able to compare the string to the U32, which can only contain numerical data. The input must press enter to satisfy read line and input their guess, which adds a new line character to the string. For example, if the user presses 5 and presses enter, guess looks like this, 5/n. The /n represents the new line. On Windows, pressing enter results in a carriage return and a new line, so /r/n. The trim method eliminates the /n or /r/n, resulting in just 5. The parse method on strings converts a string to another type. Here, we use it to convert from a string to a number. We need to tell Rust the exact number type we want by using letGuess U32. So we need to specify U32. The colon after guess tells Rust we'll annotate the variable's type. Rust has a few built-in number types. The U32 seen here is an unsigned 32-bit integer. It's a good default choice for a small positive number. You'll learn more about other number types in chapter 3. Additionally, the U32 annotation in this example program and the comparison with secret number means Rust will infer that secret number should be a U32 as well. So now the comparison will be between two values of the same type. The parse method will only work on characters that can logically be converted into numbers and so can easily cause errors. If, for example, the string contains an emoji and ampersands and stuff, there will be no way to convert that into a number. Because it might fail, the parse method returns a result type, much as the read line method does which we discussed earlier. We will treat this result the same way by using the expect method again. If parse returns an error result variant because it couldn't create a number from the string, the expect call will crash the game and print the message we would give it. If parse can successfully convert the string to a number, it will return the OK variant of the result, and expect will return the number that we want from the OK value. Let's run the program now. Let's do it. Cargo run. Please input your guess. 88. Too small. How about I put some string? Fair enough. We got it to panic and everything. So let's put some garbage in there. Please type a number. So that's cool. We're getting the proper errors. Nice. Even though spaces were added before the guess. Nice. Even though spaces were added before the guess. Nice. Even though spaces were added before the guess, the program still figured out that the user guessed 76. Run the program a few times to verify the different behavior with different kinds of input. Guess the number correctly, guess a number that is too high, and guess a number that is too low. We have most of the game working now, but the user can make only one guess. Let's change that by adding a loop. Allowing multiple guesses with looping. The loop keyword creates an infinite loop. We'll add a loop to give users more chances at guessing the number. All right, so let's do that. Loop, open, and then we'll indent all this stuff. There you go. And then what? We close it here. Nice. As you can see, we have moved everything from the guess input prompt onward into a loop. Be sure to indent the lines inside the loop another 4 spaces each and run the program again. The program will now ask for another guess forever, which actually introduces a new problem. It doesn't seem like the user can quit. My users are not quitters, so that's alright. The user could always interrupt the program by using the keyboard shortcut Ctrl-C, but there's another way to escape this insatiable monster, as mentioned in the parse discussion, in comparing the guess to the secret number. If the user enters a non-number answer, the program will crash. We can take advantage of that to allow the user to quit, as shown here. Alright. Typing quit will quit the game, but as you will notice, so will entering any other non-number input. This is suboptimal to say the least. We want the game to also stop when the correct number is guessed, quitting after a correct guess. Let's program the game to quit when the user wins by adding a break statement. All right, so when it's equal, we'll go ahead and add the semicolon here, and then break. Adding the break line after you win makes the program exit the loop when the user guesses the secret number correctly. Exiting the loop also means exiting the program because the loop is the last part of main. Handling invalid input. To further refine the game's behavior, rather than crashing the program when the user inputs a non-number, let's make the game ignore a non-number so the user can continue guessing. We can do that by altering the line where guess is converted from a string to a U32 as shown in listing 2-5. If they input a number that we can parse, then we assign that to guess, else we'll continue, which means that we'll request another number. So let's type that up. We switch from an expect call to a match expression to move from crashing on an error to handling the error. So that's pretty good. Remember that parse returns a result type, and the result is an enum that has the variants OK and error. We are using a match expression here, as we did with the ordering result of the CMP method. If parse is able to successfully turn the string into a number, it will return an OK value that contains the resultant number. That OK value will match the first arms pattern, and the match expression will just return the num value that parse produced and put inside the OK value. That number will end up right where we want it in the new guess variable we are creating. If parse is not able to turn the string into a number, it will return an error value that contains more information about the error. The error value does not match the OK num pattern in the first match arm, but it does match the error underscore pattern in the second arm. The underscore is a catch-all value. In this example, we are saying that we want to match all error values, no matter what information they have inside them. So the program will execute the second arm's code, continue, which tells the program to go to the next iteration of the loop and ask for another guess. So, effectively, the program ignores all errors that parse might encounter. Now, everything in the program should work as expected. Let's try it. All right, let's try it. Why not? Cargo run. Then go get coffee or something. Okay. Please input your guess. So I'm going to say 23, too small, 24, you win, and the game ends. Please input your guess, some crazy text, and then boom, what happened? I bet you that I screw up somewhere. Oh, I know what it is. I have to move this line in here so that we can actually see the error. Please input your guess. You know what will be better? If here in the error, let's just print the error. Why? I mean, I don't understand why not printing the error. It's just confusing, in my opinion. Print line error. That way, when the parser fails, now we'll get a human readable error. Error, invalid digit found in string. Much better. I like my program better, to be honest. But maybe that's what we were about to learn in Rust. Let's see. Awesome. With one tiny final tweak, we will finish the guessing game. Recall that the program is still printing the secret number. That worked well for testing, but it ruins the game. Oh, it ruins the game. Let's delete the print line that outputs the secret number. Listing 2-6 shows the final code. At this point, you have successfully built the guessing game. Congratulations! Summary: this project was a hands-on way to introduce you to many new Rust concepts. Let, match, functions, the use of external crates, and more. In the next few chapters, you'll learn about these concepts in more detail. Chapter 3 covers concepts that most programming languages have, such as variables, data types, and functions, and shows how to use them in Rust. Chapter 4 explores ownership, a feature that makes Rust different from other languages. Oh yeah, it does. Chapter 5 discusses structs and method syntax, and Chapter 6 explains how enums work.